I have with my postdoc Greg Wilsonak on arithmetic circuits. It's to be presented in a couple of weeks' time at the iCalc conference. And leading up to that, I'll tell you a little bit about notions of symmetry we've been looking at in classical Boolean circuits and so on, and maybe end with some questions about how these notions of symmetry might appear in the context of quantum circuits. Okay. So Robert said in his introductory remarks that this is the audience is from varied backgrounds. So I thought I would start with kind of a basic view on complexity theory, computational complexity, where we study complexity classes such as P and NP. And it is kind of standard to look at these complexity classes as sets of decision problems. So where the decision problems meaning things which get a yes or no answer. And to make this mathematically precise, we identify a decision problem with a set of strings over a finite alphabet. So we have some finite alphabet and a collection of strings. And it's the membership problem deciding whether a string is in the set or not that we look as a decision problem whose complexity we're analyzing. To be even more concrete, we will identify the fixed finite alphabet. We'll just take it to be the two-letter alphabet with 0 and 1 in it. And then we get definitions like of P and NP. P is those languages which are decidable by a deterministic Turing machine running in polynomial time, or NP is languages decidable by a non-deterministic Turing machine running in polynomial time. But I'm leading up to talking about circuits, which is a different view, because even with all this simplification, things like Turing machines are sort of mathematically quite complicated things to define, let alone to try and prove impossibility results about, which is what we want to do. So another view of a language. Now, a language is a set of strings over the alphabet 0, 1. So one view is to slice it up according to the length of the string and look at, for each length n, at the function which takes strings of length n and gives you an answer yes or no, which we think of as 0, 0, or 1. So each of these is now a finite Boolean function. And any finite Boolean function can be computed by a circuit where we have operations, simple Boolean operations, and or not is sufficient. The inputs are x1 through xn variables which can take values 0 and 1, and we have a distinguished gate determining the output. So the circuit as a whole computes a Boolean function. The hope is, of course, that it provides one possible route to proving lower bounds for hard problems. I mean, this was, I suppose, back in in the early days, 1980s, 90s, the great hope of circuit complexity kind of eventually foundered. But then most efforts at proving real strong lower bounds, like separating P from NP, have foundered somewhere or the other. So intuitively speaking, a circuit is just the unfolding of the behavior of an algorithm. You fix the input size to be some number n, and then you just, the algorithm, you break it down into simple steps and or not. So, a circuit looks something like this. Each of these, does this work? Yes, okay. Each of these input variables takes a value 0 or 1. We get, and we apply a certain sequence of functions, and then we have an output over here, which is a single bit, which tells us whether the particular string of zeros and ones is in the language or not, okay? The reason for considering circuits is because we're interested in lower bounds, in impossibility results. So the hope is that the combinatorial simplicity of circuits allows us to prove lower bounds. There is a cost in that circuits are a non-uniform model, so we've lost something here. And in the context of P versus NP, I would explain this as follows. Consider those problems for which, for each value of n, there is a circuit of size polynomial in n, which correctly decides the problem. This is usually called the class P/poly, the non-uniform version of polynomial time. The non-uniformity comes from the fact that the different circuits at different sizes might have nothing to do with each other. There's nothing that says they're all generated from the same algorithm. But the conjecture is that nonetheless, NP is not included in P/poly. This is, of course, harder conjecture than separating P from NP, because I mean, it implies in particular that P is different from NP. And in some sense, it can be understood as the following claim. That is, if you have an NP-complete problem, it's one thing to say there's no polynomial time algorithm. To say that there's no polynomial size family of circuits says that let's allow the following protocol. We have an NP-complete problem. I'll only tell you the size of the input. And after that, allow you to do an arbitrary amount of computation. You can do anything you want to prepare. And then I give you the actual input, but from that point onwards, you do a polynomial amount of computation, right? That's really what P/poly is. The preparation of the circuit can involve anything. I mean, I say arbitrary amount of computation. It doesn't even have to be computable, okay? Okay, so that's P/poly. Now, in the quest for lower bounds, I want to talk about the particular view we've taken, which is really the decision problems we're interested in. We've been going down to the circuit model and thinking of them as strings of zeros and ones. We've hidden something, which is that we're often interested in decision problems on abstract combinatorial structures. And for me, the classic example is things like graphs. The input is a graph. Is it connected? Is it three-colorable? Does it contain a Hamiltonian cycle? Does it contain a perfect matching, etc.? Those are the kinds of problems we write algorithms for. So how does that translate into the circuits? Well, first of all, we assume always that you can encode a graph as a string of zeros and ones. For instance, take the adjacency matrix and enumerate it in some fixed order. When you do this, the trouble is, of course, that a given graph may be encoded in many different ways. I say some fixed order. To turn the graph into a matrix, you have to order the vertices in some way. If there are n vertices, there's n factorial potential orders. They can give you all distinct strings. I mean, if the graph has automorphisms, it'll be fewer than n factorial, but up to n factorial distinct strings representing the same graph. So let's say two strings are equivalent if they represent the same graph, which is to say, okay, I'll come back to what that means more precisely. But really, it just means we can reorder the vertices of the graph to get y from x. And we say that a Boolean function is invariant under this if exactly what it says. On equivalent strings, it gives you the same answer. This is what we would say that a Boolean function that really is deciding some property of graphs rather than of strings. Okay, so now a property of graphs is recognized by a family of Boolean circuits. So the inputs are the potential edges of the graph. There may be, let's say, on an n-vertex graph, n squared of them. If we're thinking of a directed graph, let's say, which may or may not have loops as well. We think of each of those as a Boolean variable xij, which will be 0 if there's no edge from I to j, 1 if there is an edge from I to j. We're still interested in polynomial size circuits. And if we want to have a uniformity, then we also say that the function that takes n to the circuit of size n is computable in polynomial time. But if we're not interested in uniformity, we can drop this last condition. And for it to be decide a graph property, the circuit has to be invariant in the sense that the Boolean function it computes is invariant under this equivalence relation, right? Reordering the vertices of the graph shouldn't change the result. Okay. This is the same as saying that if on these n squared, this set of n squared inputs, you apply a permutation on n, the result should be unchanged, right? So what do I mean by apply a permutation on n? Apply the permutation on these n squared inputs, which takes the variable xij to x pi I pi j. So you apply the same pi to both coordinates. Now, so this is not an arbitrary permutation of the inputs. It's a particular group action. The action of the symmetric group on n on these n squared inputs. It's a sort of natural group action. Okay. Now, I give this sort of as an introduction. Now, in the context of circuit complexity, I said there was a sort of big excitement in the 1980s because there was real lower bounds proved, and lower bounds were proved by restricting the circuit model in various ways. Probably the first such successful one was Rasborov's results on monotone circuits, and the point is that these were actually about graph properties. So some graph properties are naturally monotone. What does monotone mean? It means if you have two graphs on the same set of vertices, one of which has strictly more edges than the other, right? So every edge in G is also an edge. Every edge in G is also an edge in H. We say the property is monotone. Examples I mentioned, so connectedness. If a graph is connected, adding more edges to it will still keep it connected. If it contains a Hamiltonian cycle and you add more edges, it still contains a Hamiltonian cycle. I mentioned perfect matchings. The same is true there. Three-colorability is kind of anti-monotone. Its complement is monotone. So if a graph is not three-colorable and you add more edges to it, it's still not three-colorable. And now, monotone graph properties in this sense are described slice-wise by monotone Boolean functions, which means you have a Boolean function where if you change an input from 0 to 1, the output cannot go from 1 to 0, right? And in principle, a monotone Boolean function can be described using only and or gates. You don't need negations. You don't need not gates. Okay, any monotone Boolean function can be so described. So the question is, how big a circuit using just and or gates is needed for monotone functions? And these were the lower bounds first proved by Rasborov. Specifically for the clique problem, you're looking for a clique of size k. In principle, there's monotone functions, but they provably need to be bigger than polynomial. So this looks exciting, but then it also turns out that the problem of a graph containing a perfect matching, you can also show has no monotone polynomial size circuits. But this is a problem we know does have polynomial size circuits in the sense that it's a polynomial time decidable problem, which means that what this is really showing is that the translation from a circuit with negation, but deciding a monotone problem to an equivalent monotone circuit can blow up the size of the circuit enormously. Okay. Now there are other lower bounds on circuits obtained typically by bounding the depth. So no constant depth polynomial size family of circuits decides parity. This classic result of first accepts. As I said, these were the sort of heady days of circuit complexity in the 1980s. Now, I mentioned a more recent result. I mean, there's still active work, and there's quite a striking result of Rossmann, which showed that for the clique problem, there is no constant depth family of circuits which decides clique in size less than n to the something. That's the order of the size of the clique you're looking for. Okay. Now I want to get to the topic that I've been discussing. We've been looking at symmetric circuits. What do I mean by symmetric circuits? So we're talking specifically about circuits for graph properties. So I should have said, so the inputs to the circuit are indexed, I'll write this, by pairs of variables. Sorry, by variables indexed by pairs in N. Okay, so we are thinking of the input as an n-vertex graph. And we say that the circuit is symmetric if you apply the permutation of Sn under its natural action on these n squared, then it can be extended to an automorphism of the whole circuit. So you can permute the gates of the circuit to get back the original circuit. So exactly what it says, for each pi, there's an automorphism that takes the input labeled xij to x pi I pi j. Any circuit that is symmetric in this sense obviously decides a graph property. It's going to be invariant under that equivalence relation I defined earlier, but the converse is not necessarily true. You can come up with circuits which are not symmetric in this sense, but where the result is still invariant. And again, so a natural question arises, translating a circuit which is invariant into one that is symmetric, you can always do this. Does it blow up the size of the circuit? And we can show it does. But that's in some sense not the main point here. We have actually a very nice characterization of things which you can decide by symmetric circuits, which turns out to be related to things we've been looking at in the context of decision problems definable in fixed point logic with counting. I'm not going to go into fixed point logic with counting at this point, but I'll just give you the characterization. So a graph property is definable in this logic formalism if and only if it's decided by a uniform family of symmetric circuits where we can use and or not gates and a majority gate. Okay, so a majority gate is simply one which takes a number of Boolean inputs and the output is 1 if a majority of the inputs is 1. You need these majority gates because if you leave them out and you just use and or and not, you get something strictly weaker. As I said, then we can show that there are invariant circuits which with just and or and not, which if you symmetrize, you get an exponential blow up. But with majority gates, you get something much more robust. Okay. It's robust in the following sense. Now consider any Boolean function, which is maybe why I should call this fully symmetric. It's invariant under all permutations. So this is examples of this are the and, the or, and majority, and pretty much anything you would use as a gate in a circuit, right? Basically any function which just counts the number of ones in its input and gives a result based on that. So the robustness argument is if instead of majority you allow any symmetric gates in your basis, you still don't get beyond the power of FPC. As long as your circuit is symmetric, these are two different uses of the word symmetric. But as long as your circuit is symmetric, in the sense it has automorphisms for all permutations of the vertices on the input, you don't go beyond the power of FPC. So it's a very robust class. And what I would say is it defines the natural notion of polynomial time symmetric computation. And now we have, here's another circuit class effectively for which we have real lower bounds. So we can prove for some NP-complete problems they're provably not doable by symmetric circuits. It includes satisfiability, which isn't a graph problem, but we can tweak it into this formalism, but Hamiltonicity, three-colorability, these are NP-complete graph problems. But there are also polynomial time properties of graphs which are not definable in FPC, and we've known this for a long time. Okay, so again, this shows that, well, this is it's a robust notion, but it's still properly contained in polynomial time. So these impossibility results don't advance us, say, towards the goal of proving real lower bounds on these NP-complete problems. Okay. Now, a quick word about how we prove these impossibility results, because this is I want to lead into my discussion of arithmetic circuits. These are tied to something which is called the Weisfeiler-Leman Equivalence relations. Again, I'm not going to define these. Here's what you need to know about them. These are parametrized by a natural number k, equivalence relations on graphs, right? So think of it as an equivalence relation, which we think of it as an approximation of isomorphism in the sense that if two graphs are isomorphic, then they're certainly not distinguished by Weisfeiler-Leman equivalence. And it is sort of graded, so the higher your parameter k, the closer you are to isomorphism. And if you take k to be as big as n, the size of the graph, then it is the same as isomorphism. So this n Weisfeiler-Leman equivalence on n vertex graphs is the same as isomorphism, and higher values of k give you closer approximations. I haven't given you a definition. It turns out there's many different definitions because this has popped up independently almost in a variety of areas. The original definition by, well, I suppose the original definition is due to Baba. It was generalizing notion from Weisfeiler and Leman, which we now will call the two-dimensional Weisfeiler-Leman. And Babai's version was combinatorial. The original Weisfeiler-Leman one was algebraic, but it can be generalized to arbitrary k. There's characterizations in terms of games, in terms of logic, in terms of linear optimization, and so on. This is a sort of family of equivalences that arises in many places. Its connection to what I've been talking about is that this class FPC of problems, which is I'm thinking of as symmetric polynomial time. It's contained inside polynomial time, but computable by symmetric circuits. Any property definable in here, for any such property, there is a k such that it's invariant under k equivalence. And this is really the method for proving lower bounds or impossibility results. To show that something is undefinable here, you show that it is not invariant under k equivalence for any k, right? And we can do this for all the examples I mentioned: Hamiltonian cycle, satisfiability, and so on. This leads us to this what I call the counting width. The name comes from this fixed point width counting. The counting width of a class of structures, class of graphs, think of it now, is the number. So with every n, there's a number k, which is the smallest value for which the class of graphs restricted to let's say n vertex graphs is invariant under k equivalence, right? As I said, so I'm assuming the class, of course, is invariant under isomorphisms. So clearly, this k is at most n, right? Or maybe I'll write this here. So nu c of n has to be at most n. So there will be a value. For properties that are definable in fixed point width counting, so decidable by symmetric circuits, this will be bounded by a constant, okay? We can do this not just for classes of graphs, but for any numeric graph parameter. So a graph parameter, I just mean something that assigns a numeric value to a graph, like the chromatic number of the graph, or the number of connected components, or various things like this. Okay, and again, for any numeric value, we can define the smallest k such that n vertex graphs are invariant under k equivalence.
Please, may I ask one question?
Sure.
I thought Shihan would say something before I asked, but I was wondering, I didn't quite understand what the k actually labels. What does it mean?
What the k labels? Okay.
Yeah, what is the k in terms of the graph or circuit?
Okay, so maybe let's go back here. So the k is labeling this equivalence relation. In the sense, for each k, we have an equivalence relation. So I didn't say how it's defined, but roughly speaking, we define there's a sort of implicit algorithm which tries to determine isomorphism by looking at the lengths of k tuples and determining that sort of k tuples locally in the two graphs look the same. And as you increase the value of k, you get a better, you get an algorithm which better approximates isomorphism. And if you actually look at k equals n, then you can enumerate the whole graph in a single tuple and actually determine isomorphism. That's why once you're looking at n equivalence, it's the same as isomorphism.
All right, thank you.
Does that help? Yep. Okay. So the point is that if you were looking at something like the number of connected components, it turns out that the counting width would be bounded by something like 2 or 3, right? Once two graphs are 3 equivalent, then they have the same number of connected components. But if you're looking at chromatic number, then there is no constant bound. In fact, you can show that the counting width of chromatic number is linear. So it's going to be some constant fraction of n, right? You need to go up to that higher dimension to be able to fix the chromatic number of a graph. Okay. So yeah, it's the smallest value of k. So that when you have two n vertex graphs, them being k equivalent implies they have the same value for this particular parameter. So if you can define a numeric parameter in FPC, which, as I said, in some sense means you can determine it by symmetric polynomial size circuits, then it has counting width bounded by a constant. And in fact, now showing lower bounds on the counting width of a parameter gives lower bounds on any symmetric circuit, on the size of symmetric circuits, even for non-uniform families. So actually, this counting width is a non-uniform measure rather than FPC, which was about p-uniform families. With that, I'm going to come to tell you about our recent work on arithmetic circuits. So this is the sort of the background on Boolean circuits, where we had looked at this relationship in counting width and symmetric circuits. So what's an arithmetic circuit? So you fix a field, and we have a circuit now where inputs are variables or constants from this field. And the gates are labeled by arithmetic operations, addition and multiplication, right? Now, if I give you such a finite circuit, it's a directed acyclic graph, the internal nodes being addition and multiplication, the inputs being variables or constants, and you have a single output. The output defines a polynomial in the ring over this this field with variables from X. In fact, we think of it really as a compact representation of such a polynomial, right? I mean, the fact that it's a circuit means you can reuse certain sub-expressions. So it's a compact representation of a polynomial. Now, in the context of arithmetic circuits, there's a sort of analog of the P versus NP question. This is posed by Valiant in 1979, who defined a sort of polynomials represented by polynomial size circuits, and those which are sort of given by projections of polynomial size circuits, which is sort of VNP. He conjectured they're different. And if P is different from NP, I think that implies that they're different. So it's a related question. And he gave an example of one particular polynomial, the permanent, for which it is conjectured that there are no polynomial size arithmetic circuits. And the problem is complete for the class VNP, which means that proving that there are no polynomial size arithmetic circuits for the permanent would prove this conjecture. So what is the permanent? It's the following polynomial. We have a matrix of variables xij, ij in n, so in a square matrix of variables. And the polynomial is the sum over all permutations in Sn of the product of xi with, of the product over all I of xi sigma I. Okay. If it looks a bit strange, of course, it is a slight variation of a much more familiar polynomial, the determinant. The determinant can be described exactly as a similar expression, except that each of the products is multiplied by the sign of the permutation, +1 if it's even, -1 if it's odd. Okay. But now the determinant. Now, if you look at the expression as written, you can write it as a circuit where you have the n squared variables on the inputs, and then you have these product gates, right? And then let's see, each one taking n inputs, but one for each sigma n Sn. So there'll be n factorial of these product gates, and then one sum gate. So it's a circuit of depth 2, but of very large size. It has, n factorial size. Same for the determinant. If I were to write this expression as a circuit, I would get something enormous. But we know that there are efficient ways of computing the determinant using Gaussian elimination, for example. And those translate into circuits. I mean, those algorithms unfold them, into the arithmetic operations, and you get a small size circuit, which computes the determinant. Okay. But the conjecture is that for the permanent, this is impossible. You can't get small size circuits to do it. Again, there are known lower bounds for arithmetic circuits, which kind of mirror the kinds of restrictions people looked at in the case of Boolean circuits. We say a circuit, now specifically over the real field, is monotone if it uses no negative constants. And it was proved that there are no, I mean, this goes back to 1982. There is no sub-exponential size arithmetic circuits which are monotone for computing the permanent. Okay. Again, bounding the depth, there are exponential lower bounds. Grigoriev and Karpinski showed this for depth 3 circuits for any finite field. But again, much like the case with the monotone and constant depth circuits for the Boolean case, these lower bounds also apply to things for which we know there are efficient algorithms. In this case, they both apply to the determinant just as well as to the permanent. It turns out that you can show that there's no sub-exponential size monotone circuits for computing the determinant. And again, no depth 3 sub-exponential size circuits for computing the determinant either. So we asked ourselves the question, what about symmetric arithmetic circuits? Because both the determinant and the permanent are defined over a matrix of variables. And these polynomials have certain natural symmetries. In particular, you look at exactly the action I was talking about in the case of graphs. You look at a permutation of n and apply it to this matrix of variables. That's the same as applying a simultaneous permutation of the rows and columns of the matrix. It doesn't change the value of either the determinant or the permanent. In fact, for the permanent, you can relax this even further. You can allow independent permutations of the rows and columns, and you don't change the value of the permanent, right? Also, for the determinant, you could relax a little bit beyond this. You could say we would allow arbitrary permutations on separate permutations on the rows and columns as long as they're of the same sign or something like that. But anyway, the point is that these matrices, these polynomials, determinant and the permanent, have rich groups of symmetries. So what about we require that the circuits respect those symmetries, as you would expect sort of an algorithm described at high level to do? And can we, with symmetric arithmetic circuits, compute these? And it turns out here we're able to prove a sort of separation between the determinant and the permanent. In the case of the determinant, we can find symmetric circuits which do it. And in the case of the permanent, we can actually prove there aren't any, right? And this is a provable lower bound. It's not conditional on complexity separation. This is the recent result that I was telling you about. So let me say a little bit about the upper bounds. So a standard way of computing the determinant is Gaussian elimination. And if you express it as a circuit, you get polynomial size arithmetic circuits, right? It's a polynomial size computation involving just additions and multiplications. But it's not symmetric, right? This is an algorithm where at each stage of the computation, you have to choose a pivot. And that's a symmetry breaking operation, because different choice of pivot will lead to different computations. You can symmetrize it by doing them all in parallel, but that gives you an exponential size circuit. Okay, so Gaussian elimination is not good for this. Instead, we consider something called Leverrier's method, which basically computes the trace of higher powers of the matrix, and then you just have to sort of, by recursive operation on these traces, you can extract all the coefficients of the characteristic polynomial of the matrix, really. And we can show that it is symmetric at least under simultaneous row and column permutation. So in other words, under the action of Sn on the n by n matrix. And I say it works in fields of characteristic 0. I think you could also make it work in any field of characteristic larger than the size of the matrix. It's just because it involves division. I mean, to make the method work, you need division by the order of the matrix roughly. So, okay, but at least there is a notion of a symmetric circuit which works at least in characteristic 0. In the case of the permanent, the best known circuit we get is from what's called Reiser's formula. I won't tell you why this expression gives you the permanent, but it does. And this works over any field. And it gives you something which is of size roughly 2 to the n times n squared. So it's still exponential. But it's better than the n factorial one, which you get from the immediate definition, right? So 2 to the n times n squared is somewhat smaller than n factorial. But the thing to note here is that this is the best known circuit, the smallest known circuit, without any restrictions. But it turns out it is, in fact, symmetric. Okay, so we don't know of any circuit that will do better than this. But the one we do know that works in this size is, in fact, invariant under arbitrary permutations of the rows and columns. If you apply it, you get back the same expression. So here is our theorem. We basically show that you can't do much better than exponential. So for any positive epsilon, there's no symmetric circuits for computing the permanent of size 2 to the n to the 1 minus epsilon. Okay, so better, strongly sub-exponential. They don't exist, and we're able to do this in any field as long as its characteristic is not 2. Note, characteristic 2 is special because in characteristic 2, the permanent and the determinant are actually the same thing, right? Because 1 is equal to -1, so the sign becomes irrelevant. So really, we wouldn't expect to get lower bounds in characteristic 2, but we get this for all other fields. Very quick outline of what the steps in our proof are. Suppose there was small circuits for the permanent. We show that we can translate these into circuits into symmetric circuits, which are now Boolean, and which compute the permanent for 0-1 matrices. Okay, so basically you can translate you just specialize the algorithm. The important thing is preserving the symmetry. We don't manage to preserve the size, but we are able to show that because we started off with size s, the size of the orbits in our circuits, by the orbits I mean under the action of these permutations, under the action of the symmetry group, the automorphisms of the circuit, we have size at most s. Then we're able to show that if we had circuits which were symmetric Boolean circuits which compute the permanent of the matrix, then we can show that the counting width is at most this, or it's big O log s divided by log n. This is just the connection between counting width and symmetric circuits that we had in the Boolean world. And then to complete the proof, we show that, I mentioned here the number of perfect matchings in a bipartite graph. That is simply the fact that if you take a bipartite graph and you look at its bi-adjacency matrix, so you label the rows and the columns by the 2 parts of the graph, and you put a 1 where there's an edge and a 0 where there's not, then the permanent gives you exactly the number of perfect matchings. This is an easy observation. And so now we construct pairs of graphs which have a number of vertices which is linear in K, which are K equivalent, but where the number of perfect matchings differs by a power of 2, by a positive power of 2. Okay. So what's the net result of this? This shows that the counting width of the number of perfect matchings is omega n, right? It's linear in n. And therefore, if log s was strongly sub-exponential, we would get a contradiction with this. Okay, and therefore you can't get s being strongly sub-exponential. And why is the power of 2 significant? Well, this shows that not only is the number of perfect matchings in these two graphs different, the number of perfect matchings modulo p for any odd prime p is also different. So in any characteristic other than 2, this difference shows up. Okay. So let me jump ahead to the conclusion slide. I wanted to show you that the restriction to symmetric circuits gives us, we've got essentially new ways of proving circuit lower bounds, and they're potentially interesting in several different. I want to say something about, is there something relevant to say about symmetric quantum circuits? I know of very little work along this line, but very recently I found on the archive a few papers. A recent paper, I say recent, I think it was posted on the archive this week by Blas and Garevich, defines an abstract notion of quantum circuit where the quantum gates are labeled by a sort of arbitrary sets of inputs and outputs rather than an ordered set. And this allows you to define a notion of symmetry like the one we're considering. Maybe more closely, I saw another recent paper in the archives, well, maybe about 6 months ago, by Ben, David, and Potter, who look at query complexity for graph symmetric functions. So they're again looking at Boolean functions, which are invariant under symmetries, exactly the ones I described. You know, if you think of the input as a graph, the permutations of the vertices, they look at the query complexity of, of determining such a function with queries to the function, and they show that under certain assumptions, you can't get exponential quantum advantage using quantum circuits. So I think this is another interesting point of connection. But yeah, I thought I would conclude with those potential connections with quantum computation. But otherwise, I'm ready to stop here and take any questions if there are.
Okay, thank you very much, Anuj. So, are there any questions?
So I can't see the Q&A. Is that?
Yeah, I'm checking the Q&A. There's nothing on Q&A, but
Okay.
I am also checking the raised hands. Currently, I can't see any.
Okay.
Okay, Anuj. So you said you want to make connection to quantum computation. I think we have time for that if you want to. I don't see any questions right now.
Okay, no, I mean, I think I see these as potential points of contact. I haven't really explored this. I mean, with Greg Wilsonak, my postdoc, we've been looking recently at this this work of Ben, David, and Potter I mentioned on the last bullet point, which looks at the older work of both Aronson, who looked at a sort of more generic, a wider notion of symmetry, and some questions of unfairness and so on. So I mean, there's a certain line of work looking at these graph symmetric functions and their quantum query complexity. It's not quite the same in the sense that our methods are really about proving size lower bounds on circuits, and I'm not sure how that translates to quantum advantage. But I guess, I mean, I think there's a real natural question about when you look at problems like this, which have natural symmetries, like graphs, or like these, matrix ones. To what extent, I mean, is it still the case that you have significant advantage in using quantum circuits over classical circuits? I mean, that's the kind of question I would like to pose.
Okay, so there's one general question in the Q&A. It's very, very general. It's, well, asks about the importance about these circuits. Why would anyone care about these circuits? I think that's a very general question. If you'd like to answer.
Well, okay, I tried to motivate this at the beginning in the sense that we're interested in impossibility results, right? I mean, we're in complexity theory, you know, sort of the overall arching question is something like the P versus NP question, which means we have problems which we think are hard, but we don't know how to prove they're hard. To prove impossibility results, you need some kind of handle on the combinatorial structure of algorithms. You want to show that there is no possible algorithm of polynomial size for computing a certain property. And to get a handle on what an algorithm is, you sort of break it up slice-wise into circuits. I mean, that's what we use. So circuits are a kind of very low-level way of thinking of algorithms. And then, since we still, you know, in order to prove impossibility results, we have to further restrict them. Restrictions include monotonicity, which people have looked at, bounding the depth. And what we're looking at is symmetry, which I want to argue is a very natural restriction in the sense that lots of algorithms we actually use are symmetric. So that's really the reason for it. I don't know if that helps.
Okay, thank you. I think, yeah, I think that's all about the questions that I can see from the Q&A and the participants. Maybe I should ask again if there are any questions. You can use the raise hand option. Robert, you are muted. You should unmute.
I'm muted. Okay. I don't know where my raise hand option is. Can I ask a question?
You don't have to raise hands. Panelists also can ask questions, by the way. I didn't remind that, but yeah.
So Anuj, permutation symmetry was very prominent in your presentation.
Yeah.
Is the whole framework kind of agnostic to what symmetry you're using? I mean, can you use smaller symmetry groups as well, get you results for that also?
Yeah, well, no, not really. I mean, in the sense, the method we have is really about, yeah, no, I mean, that's a very good question. That's on our agenda to look at, you know, to what extent can we further restrict the symmetry groups? So the key to the method, I mean, the key that we get, which connects our symmetric circuits to what I call counting width, roughly going back, is this idea that if you look at the action of the permutation group on say vertices of the graph or the rows or columns of a matrix, and it has to extend to an automorphism, and the orbits have to have size something small like this, then basically the stabilizer group of every gate in the circuit is fairly large because its orbit is small. And then we show, because it's large in the whole symmetric group, there is actually a large subset of n on which arbitrary permutations fix this gate. And the complement of that large subset is a small set, which is where we get this value of k, the counting width. Okay. So this is very much dependent on the fact that we're dealing with the symmetric group. And I don't know how to make this work for other smaller groups.
Anuj, there's a symmetry-related question from the audience. Austin Daniel asked,
sure.
Do we expect any of these lower bounds to hold under a weaker symmetry restriction on the circuit? That means that's subgroups of the permutation group.
Yeah, I suppose I think that's the question that Robert just asked, right? Yeah. So our methods are very much based on this on the symmetric group. So I don't really know.
Okay, thank you very much. I think these are all questions. I can't see any other. Okay, thank you, Anuj.
All right.
We are going to start the next talk in 5 minutes, 8:55.
See you in a bit.
Yes. Samson, would you like to switch to your screen and see
Sure.
your slides?